It's my great pleasure to introduce today Chris Tully, my longtime friend since our undergraduate days, as the first speaker of the 2021 colloquium series hosted by the Department of Physics and Astronomy at University of Louisville. Chris Tully earned his PhD in high energy physics from Princeton University and his BS from Caltech. He is a professor of physics at Princeton University, where he also served as associate chair for the physics department. His group leads the development of novel methods for proving new physics at the energy frontier, experiments at Fermilab and CERN. He was awarded NSF, CERN, Sloan, and IBM Einstein fellowships. Although collider physics is a fundamental probe of new physics, that's not the whole story. Today, Chris will tell us a new story, the one about detecting neutrinos from Big Bang from a new experimental effort that he is leading called the Tully. So let's hear about it. Chris?
Thank you very much. It's an honor for me to speak here. And I have to say that when Swagato Banerjee and I were students together, one of the things we did at the large E plus E minus collider at CERN, our experiment did, was to measure the number of neutrinos. And based on the standard model expected couplings, we measured it to about 1%. And that, sort of 1% confirmation of the number of light neutrino species is a powerful tool that's used in early universe cosmology to look for additional relativistic degrees of freedom. And this experiment I'm proposing is very much in the same light. The idea is to measure something that we can know in the lab, and then to use that to try to understand better the sort of great advances in precision cosmology that have been occurring and are coming our way. Sort of a view with the Earth at the center and different sort of concentric spheres, where when we view the optical light that was emitted at the surface of that sphere and see it on the Earth today, we see the different objects. The objects that are on the closer spheres have been subject to gravitational clustering, so we see a lot of luminal objects. And as we look farther and farther, light from farther and farther away, we see less and less structure, and in fact at some point we see the farthest distance in which light can have traveled, because the universe was not optically transparent before that point. And that's shown here as this outermost sphere, which is when the light was emitted from there, it was in the optical, like looking at the sun, around 2700 or more Kelvin. But the universe has expanded by roughly a factor of 1,000 between the time the light was emitted from that surface to when it reached the Earth, and so it's now a black body distribution with a peak of 2.7 Kelvin. What we know is the temperature of deep space, and it's seen in the microwave. So that's the cosmic microwave background radiation. What I had mentioned earlier was that this on the right is it's this view which is kind of more of a pre-Copernican, view of the universe. Is we're actually in the middle in some sense, in that we're uniquely the oldest part of the universe that we can observe. Everything we see from the transmission of light is younger. The moon is roughly a second younger. The sun around 500 seconds younger. Saturn maybe a little over an hour younger. And so this method of collecting signals and from the skies is really sort of telling us about what the universe looked like at an earlier point in time where we are today. And so that's what we're trying to learn when we find probes that propagate this expanding universe of ours. And so the reason I can tell you that this cosmic microwave background radiation was emitted at roughly when the universe was factor of 1,000 closer to each other, is from the very successful history of precision cosmology that first detected this radiation in 1965, but then started to see the fluctuations of hot and cold spots in the mid 90s, and with COBE and successively with WMAP and Planck and other Earth and balloon-based measurements to higher precision. They've told us a great deal of physics. They've told us when the different, if you will, modes started to propagate within this hot plasma at the point we called matter radiation equality, which I'll talk about in a second. But what I want to talk about in this talk is trying to look back when the universe was a billion times or over a billion times closer to each other. And that happened about roughly 1 second after the Big Bang. And at that point, the universe, roughly 50% of the total energy density was in the form of neutrinos. And the neutrinos, what we say, decoupled at that point. That's the point in which the density of the universe dropped enough. I think it was a roughly metric ton per cubic centimeter at that time. It dropped enough for the neutrinos to start to stream through the matter and that was there. And because there is this sort of consistent picture of how the components of the universe evolved as it expanded, we know from the detection of the microwave radiation a lot about the neutrinos. We know that their number density today per unit species is roughly 112 per cubic centimeter. We also know, as an equivalent temperature that they have, if we were to look at the spectrum of momenta as they arrive on the Earth, it peaks a little bit colder than the photons, because it turns out that, as shown in the next slide, there's a reheating of the photons just after the neutrinos decoupled. But there's a lot of things we know about this process that are important. One is that neutrinos, when they're interacting very strongly with matter, they were scrambling protons and neutrons. So you could never have a bound state nucleus. And if the universe had waited, on order 15 minutes, the neutrons would have decayed away, and we would have no interesting isotopes left in the universe. So it was important that the universe cooled rapidly enough so that the photodisintegration of deuterium rate dropped, and then neutrons started to end up in light elements. And that's the process we know as nucleosynthesis. And so the neutrinos had to decouple before that time, and it turns out that is a sort of critical stopwatch. And another interesting thing, which I'll discuss a little later, is that you can also tell when you detect the neutrinos today that they were produced relativistically and not in this way, and not non-relativistically, because the dispersion of their velocities is linear in temperature, as opposed to like the square root, which you would get if you have sort of 1/2 mv squared equal 3/2 kT from a non-relativistic system. So I call the period in which the neutrinos decoupled an elementary particle phase of the early universe, maybe the last epoch of that, in the sense that it still had antimatter, a fair number of antimatter abundant everywhere in the form of positrons. And then, so these are all, light objects with a lot of energy in what we call the photons and the neutrinos radiation, because they're all relativistic. Their masses are not important. And after the positrons and electrons annihilated, they reheated up the photons. That's why there's this difference in temperature between the CMB and the CNB. And at that, about 1 minute after the universe Big Bang, then the effects of the interactions of the neutrons and photons on the matter that's also there was low enough that light nuclei could be synthesized. And then, much later, 75,000 years later, the stretching out of the universe as it expands, cooled down the neutrinos and the photons, but the matter, baryons and dark matter, their energy density doesn't drop off as fast, because if you expand the space they're in, it still goes like the sort of number density in terms of the mass of those objects. So there's a point in which the matter started to become to dominate in the universe. And this point in particular is very important, because this is the point in which you can have sound waves in the early universe, because you have to have some massive object that's moving back and forth. And so the fact that the neutrinos are still a good 20% of the energy density means that we knew that they were active at that point. That's also, this method is also, as I mentioned with the counting of the neutrinos, also the way we look to see if there was other forms of light particles that we don't know about that played a role. It doesn't appear that there are. But as the universe expanded, eventually the neutrinos became non-relativistic, or at least some of them. And so what I want to sort of guide you through is what we can learn about the universe from studying the present-day non-relativistic neutrinos, the ones that we call the Relic neutrinos, that decoupled early at 1 second from the early universe. And so on the left here, I have the Earth right there on the left, and the cosmic, the surface of last scattering for the CMB on the right. Now the scale here might look a little weird to you, because the age of the universe is roughly 13.7 billion years, and the cosmic microwave radiation was emitted about 380,000 years after the universe. But you can see I show this as 46 billion light years away, and that's because that while the light was traveling, the universe continues to expand. And so, for the light that I observed today from the CMB, if I asked how far away that surface is now, it's this much larger distance. In the case of the massive neutrinos, they start out relativistic, so they travel some distance, and then they slow down. And so you have this slow velocity. Now, if the lightest neutrino might be massless, so in fact, you could ask how much farther away would it have been emitted if we were to detect it today. It's not much farther. Universe was pretty small at that time, so it's maybe a half a billion light years away, which is like 1% of the scale. But for the massive neutrinos, it turns out that they're a lot closer than one might expect. So even for the masses that we know that there's a minimum mass of the size of 0.05 electron volt, or 50 milli-electron volt, even for that mass, the distance of last scattering, if you were to ask what's the equivalent distance that that neutrino emitted from that surface would arrive at the same time that a photon from the cosmic microwave background would arrive, that's only about 8 billion light years away. So it's really has a great impact when the neutrinos slowed down. It took them quite some time to make its last journey to Earth. And so why is that interesting? Well, it's interesting in the fact that it's still probing the universe at this very early time, but it's actually probing at a spot in which we can actually see what the matter distribution looks like at a much later, 6 billion years later, when gravitational clustering began to settle in. We can sort of use what we see there and estimating how much dark matter is around it to sort of see if there's a correlation between the fluxes we see in the neutrinos. But let me talk just for a moment, just to let you know where big questions are in cosmology, to talk about this scale, the 0 to 46 billion light years. So how well is that known? So this is a rather newer topic, but I think it will continue to be relevant for many years. And you could frame it in terms of a paradox. And one of the of understanding the universe is to the fact that it is expanding. And although we refer to what we call the Hubble constant, what that really means is that's the the present day value of how fast galaxies are receding from us. So if we were to look, 2 megaparsecs away, or let's say a few million light years away, let's say at Andromeda galaxy, we would expect that this galaxy would be receding from us at roughly something like 70 kilometers per second times the number of megaparsecs. And if we use two methods for determining this expansion rate, then we have to understand that the expansion rate isn't actually constant. So it has this U-shaped curve, and so you have a determination that you can make from how the light propagated from the surface of last scattering to our observation today. And the reason the expansion rate changes as a function of time is because what's making up the energy density of the universe is changing with time. The radiation component is cooling off, and another important effect occurs in the last sort of half of the lifetime of the universe, which is we've seen that another component, dark energy, has started to take over. You can see roughly 7 billion years ago, and is now dominant. It's now 70%, and it's this tracking of the rate of expansion or recession of type 1a supernova and other structures that we can see that the dark energy there, and that we can also see it in again tracking the light from the CMB. But if you look at objects that are closer to the present day, and you base all of your expansion measurements based on those, you get now what's considered a significant discrepancy between the two numbers. So this 73 versus 67, both of which are sort of 1% or a couple percent precision. It might be telling us something. It might be telling us that something is happening to these dark energy and dark matter components that changes the shape of this curve. And that's, if you look at the region in which the neutrinos became non-relativistic, we know that they became non-relativistic after the microwave radiation was emitted. And so, they, in some sense, what their history, the information they contain, might tell us a lot about this paradox. So if you imagine that their gravitational potentials that the neutrinos are traveling through in their geodesics on their way from the last scattering to us, then if there was a kind of a hill increase, let's say they're climbing out of a gravitational well towards us, then what happens is the neutrino flux sort of piles up in that region. And you would say, well, but you have to be looking on very large distances, and gravitational wells are like galaxies and things like that. But there is a component of gravitational potentials, which is one that's very important to our fundamental understanding of the very earliest universe, which are perturbations of space-time, curvature perturbations, which have been stretched out to the scale of the entire sky. And we know this theory is inflation, and we believe that these sort of perturbations were always occurring before the Big Bang occurred. And when towards the end of inflation, suddenly some length scale was reached in which matter and radiation was created, but the universe was extremely flat in this because of the inflation. But the small perturbations that remained, that's what helped seeded the fluctuations of the CMB. And then for the neutrinos, it turns out that they would also see such perturbations, but in some sense at much smaller wavelengths or sort of higher energies than the CMB because they were emitted so close to us. And so if you look at the distances in which the effects of gravitational potentials have affected the neutrino flux, they're actually very close to us. And that provides an interesting way of looking at the universe. So when we look at the universe through microwave backgrounds, we see, sort of scales that are on order 150 megaparsec that sort of seed galaxies and produce structure. And we know them in terms of the so-called acoustical waves when we study the sort of anisotropies, the hot and cold spots on the sky. For the neutrinos, it's very different. So because they're produced so close to us, when the massive ones, we really see just those large-scale perturbations that are between us and that last scattering center. So we really see just very big, like dipole anisotropies. So if we look at one direction, we would see less neutrinos than if we look at 180 degrees in the other direction. And that difference in flux, the distribution of those differences, is a direct measure of the inflationary weights that are still, part of the universe today. So, so this is sort of the ultimate goal before I talk about the experiment, which is that we're hoping to be able to make images of the neutrino flux on the sky with polarized targets. And because they really are imaging gravitational waves that are within the region that are now being mapped by Sloan Digital Sky surveys and for future Euclid and other LSST and other surveys, the dark energy survey, for instance, there might be this interesting ability sort of really to learn whether in that U-shaped region of the universe expansion, whether the integrated dark matter potentials, which the neutrinos are sensitive to, really behave like we expect them to. So how, that's all wonderful and great, but how do you actually measure the cosmic neutrinos? They haven't only been determined based on their contributions at matter radiation equality and a little bit towards the end in recombination. Their flux is huge. It is many, many orders of magnitude larger than the flux of neutrinos coming from the sun. The neutrinos coming from the sun, the lowest energy peak is around 300 keV, but the momenta of the Relic neutrinos, because of the expansion, is very small, less than roughly 0.1 millielectron volt. So they have very little energy, and they don't interact very strongly. In fact, the strength of the interaction of neutrino goes roughly increases roughly like the energy squared until for low energies. But there are nuclei that can capture them. This is the tritium nucleus, the heaviest hydrogen nucleus that can beta decay into helium-3 and electron and neutrino. And it turns out that by crossing symmetry, the same process can absorb a zero momentum or very low energy electron neutrino, or a massive neutrino that has some fraction of electron flavor, and it's a 2-to-2 process. So it produces an electron and a helium-3. So if you look at the kinematics of that process, then what you see is if you study the beta decay spectrum, where you're looking at the energies of electrons coming from just tritium from its 12-year half-life, then it's a spectrum that falls off at roughly 18.6 kiloelectron volt. But if you look very close to the endpoint, at the sort of hundreds of millielectron volt scale, then you hope to see some neutrino mass observables. And in fact, this is the primary way in which people are trying to measure, such as the Katrin experiment, which is operating now, the neutrino mass. They're sensitive at this point at just under 1 electron volt, so nearly, just twice out of the scale, so they're getting closer. Our goal was to develop an experiment that could measure at this endpoint with the precision of roughly 50 millielectron volt. And why is that important? Well, because we know from cosmology and these other constraints that the sum of the neutrino masses appears to be less than an electron volt, in fact, about less than 0.2 electron volt. And we know from oscillations that there's at least some electrons that are 50 millielectron volt. We don't know the absolute energy scale of the electrons or how they're arranged in their, so what we call the hierarchy. But with that said, we still have a very well-defined experimental goal. And this actual idea was originally proposed in 1962, not because neutrinos were massive, but the idea was maybe the vacuum was filled with so many neutrinos that it would actually Pauli block the tritium endpoint, and you would start capturing them. But with time, it was realized with massive neutrinos that this process would mean that the finite mass in the neutrino could be an energy scale that experiments could be sensitive to. So what we designed Ptolemy is an experiment that is essentially trying to make a massive neutrino observable that measures the kinetic energy of electrons from neutrino capture on tritium to roughly a part per million. And that sounds like a daunting task. And the technique that we use, it's so there's two sides of it. One is that the measurement resolution has to be very precise. The energy observable itself has to retain the mass information of the neutrino, and the rate is very small. So for roughly 100 grams of tritium, you would have only about 5 to 10 events per year retained. So given the very big orders of magnitude involved, one had to design an experiment that's very different than the sort of the conventional neutrino mass experiment. We had to design an experiment that sort of dynamically takes electrons coming off of tritium, senses that the electron is near the endpoint while it's propagating through kind of an electromagnetic trap through its RF radiation from a single electron. And on the time scale of hundreds of microsecond or roughly a millisecond, to dynamically configure a filter that would then drain the kinetic energy of the electron in favor of potential energy down to the level at which we could estimate it with the RF system, which is roughly a few electron volt, and then use a precision calorimeter at the end to make sort of an order 1% measurement of that remaining kinetic energy to be in the range of 50 millielectron volt. And the voltage difference between the calorimeter and the target has to be held that precise to roughly 10 millielectron volt on 18 kilovolt, but that's been achieved. And so it's these elements in between that Ptolemy has been developing over the last several years, and I'll tell you what kinds of success we've had. There's a lot of interesting science in the experiment. There's material science of the target, which I'll talk about a little. There's the RF sensing at this fraction of a femtowatt radiation levels in the roughly 26 gigahertz range. There's a novel new way of filtering electrons near the endpoint so that you can look at this very precise fraction of an electron volt window just above the tritium endpoint, and this precision electromagnetic calorimeters to measure electrons of these energies. So let me just step through some of the things. Let me first talk about what one of the main limitations are for this kind of measurement, and one of them is a quantum limited motion. So if you took, the minimum potential, you would need to constrain a tritium atom and expand it. That would be a parabolic shape. It would be a harmonic oscillator, and we know that harmonic oscillators have a a ground state energy, which is h bar omega over 2. And so the motion, it's maybe best understood in a semi-classical understanding of what the ground state energy means for a harmonic oscillator. And the semi-classical understanding is that this is made up of a component that's potential energy and a component that's kinetic energy. And so it's sort of the Heisenberg uncertainty relationship, which sort of tells us the spread of position that corresponds to a given spread in momentum. But what happens is, if a particle's in its ground state, you don't see the 0-point motion. But if it interacts with something, then at the time of that interaction, what we call the 0-point motion is visible. So what's relevant in this case is this kinetic energy term, the delta p squared over 2m. And so then you can just ask the question, when the neutrino captured, the tritium captured the neutrino, emitted the electron, what was its center of mass frame velocity relative to the lab frame? And that spread is this 0-point motion. And so what you want to do is you really want to minimize or make the well very shallow so that the target atom is delocalized. So it means smaller omega naught. And we've been working on that for many years now. So a standard experiment, the Catron experiment, uses diatomic tritium, which is it's a covalent bond between two tritium atoms, and it's a strong one. It's 4.7 eV, and that turns out to impose a 0-point motion of roughly 340 millielectron volt, which is already an order of magnitude roughly larger than the energy scales that we want to get to. So we spent quite some time studying putting tritium on graphene, which has roughly a factor of 4 lower covalent bond. It doesn't, if you will, deflect as much when the atom binds to the carbon surface, and it's roughly a factor of 2 less in the plane, out of plane direction. But we were looking for materials that have more two-dimensional mobility, because as I'll describe, we're most sensitive to the electrons that are coming out at a high angle, high transverse direction with respect to overall magnetic field. And those, like cryogenic gold, cryogenic copper, you can really have kind of a two-dimensional fluid of tritium on that surface. But another one that has come up that's very interesting is that atomic physicists that study ESR of single hydrogen isotopes will put the atoms, dissociated atoms, into superfluid liquid helium. And so this is kind of an impurity. So the impurity gets coated with a kind of atomic layer of helium-4 with van der Waals force. The helium doesn't exchange electrons with it. And these little kind of matrix or little flakes, you can actually store a lot of free radical atoms in this way. And so we're investigating this technique because that actually might be ultimately well below the requirement that we need for our experiment. With regard to the radio frequency detection, we have this has been successfully done, I should say, by it was invented by an experiment called Project 8, and they successfully have measured the tritium endpoint spectrum using frequency. And so you might, I didn't put an explanation slide here, but essentially, if you put an electron in a magnetic field, non-relativistic electron, you know what its cyclotron frequency is. And for 1 Tesla magnet, it's about 28 gigahertz. But this cyclotron frequency has a relativistic correction. So if the electron that comes from the endpoint of tritium is going about a fourth of the speed of light, it has a gamma of that reduces that frequency down by roughly 4%. So it's down at roughly 27 gigahertz. And so by measuring, somehow keeping that electron in your antenna region long enough, because delta frequency, delta t is approximately 1, so the longer delta t, the higher precision on the frequency. And if you can measure this frequency to better than, you even want to do better than a part per million on it, you can try to measure the endpoint spectrum even more precisely. We do something simpler. What we want to do is just, we don't think we'll be able to keep the electron that long. And so what we use is a kind of tracking system. So if you imagine the electron is coming from a target on the left, we introduce a configuration where, in this case, the magnetic field is vertical. The electron goes in cyclotron motion, and then we have a potential well that bounces it back and forth. And then we use these techniques called second-order drift terms that allow the electron speed, the drift speed from left to right, to be very slow. So I can actually drift the electron over a region of tens of centimeters at a rate of almost as slow as 50 meters per second by just using small voltages. And this buys us the time we need to set up this dynamic filter, and it also allows us to accumulate the signal we need. If we plug in what we would call the Dickey radiometer equation, we need at least 10 microseconds of RF radiation to get the signal to noise we need to see the RF signal. And that process is working well. We simulate it. This is a simulation in the bottom left of electron going back and forth. Its little blurb is its cyclotron motion, and the back and forth is the longer distance bounce motion, left and right. And so on the bottom right plot, where we show the blue and the orange and the blue, this is just the back and forth motion, what we call the parallel component, the momentum of the electron along the magnetic field line. And so it really works like a tracker. So we measure the momentum by its along one direction, the parallel direction, and we can actually measure the total energy of the electron by this relativistic correction to the frequency. So we get both the transverse and the parallel components. But since we're only looking at the endpoint, we can always assume, based on the parallel component, how to set up the filter. So we have some ongoing studies. Let me talk about the filter. The filter was a new invention made for Ptolemy. We're in the process of prototyping it now. This is a magnet that's going to host the first system that will take the electrons of 18 keV down to a few eV in a distance of about 40 centimeters. And it has this funny structure. So, in some sense, there's a standard U shape or C shape magnet that's returning the flux between the pole faces. These big aluminum pieces are just coils. And then there's these funny arms that come around. And the arms are actually controlling the fringe field in the region of the filter. And so when we study this, what we're trying to do is create a configuration in which we can balance small differences across the cyclotron radius of the electron. So if you imagine that when the electron goes around in its small orbit, which is at 1 Tesla is only about 0.4 millimeter, if there's a small voltage difference on the top of that orbit versus the bottom, it actually causes the electron to drift a little. We call that E cross B drift. And if there's a small difference in the magnetic field, then the cyclotron radius is slightly different on one side than the other side. We call that gradient B drift. And so we have to make a configuration that, if you look up at the top right, there's a kind of a red and a green patch. That is the electric field generated by electrodes in that region. And if we look in decades, you can see it sort of moving out. So it's just constant. It's actually dropping exponentially along that line. And similarly for the fringe field from the magnet, if we look down the bottom left, there's a little green patch on the side. When we look at different scales of magnetic field from 1 Tesla down to about 10 Gauss, we're dropping both fields at the same time. So I won't try to describe how the filter works. These filters are always complicated. My colleagues have often said that they worry that my design here for the magnet looks a little bit too much like a Star Trek bird of prey, but that was not intentional. But to give you kind of a notion of how it works, is that if I show here on the left the trajectory of the electron, where the red is 18 keV and the blue at the very top is the sort of 100 eV scale, then the trick is that you introduce these additional fields and gradients that kind of steer the electron up a potential. And it's very much like if anyone ever tried to ski up a hill. If you try to go straight up and just push, good luck. If you sort of bounce left and right, it's called the Herringbone Technique. It's very similar to how we drain the parallel and transverse kinetic energies in this electromagnetic system. But we find it's a very powerful technique. We think it'll be quite important. So looking at the calorimeter just briefly, we have the world's most precise TES for infrared photons. It was developed in the INRIM Institute in Torino in Italy. And they can count infrared photons, and very quickly, even though it's a TES, where normally the time scale response is hundreds of or tens of microseconds. This one is sort of up and down in 120 nanoseconds, because low energy electrons need very little thickness of material, very little capacitance to measure them. And so the new design is able to achieve a full width half maximum of 22 milli-electron volt at infrared energy 0.8. And so we're testing that with electrons. And so we'll be very excited if we have the world record for electron measurements too. So that last couple orders of magnitude, that's the key part of the final energy measurement. So that's what takes us from going from, we have a precision voltage difference that is a fixed value, and that little difference relative to that we measure with the calorimeter. And then we have to know what the trajectory was of the electron, because it did lose radiation while it went through the tracking system. So on the left is a view of our R&D area at the Gran Sasso National Laboratory in Italy. And you can see maybe the RF setup in the far left there. We have a set of superconducting magnets and a large vacuum tank that was made for configuration, was similar to Catrin, but we've adapted it for our transverse filter. We have a dilution refrigerator where we mount the TES system, and we're going to have a fully operational prototype in the coming year. Right? When things get back to normal, we've started fabrication at the different institutes, and that's going well. So this project so far has been funded, very thankfully by the Simons Foundation. That's really made all of this work possible. But recently, I have to say, we've had groups from Europe who've been able to join with their own funding. This is a link to a nice, if you want to practice your Dutch, an interview with my colleagues on their, I think the interview is about a baby photo of the universe. You can almost see that here in Dutch. And then the INFN with the R&D area at the LNGS has been essential. We've published a couple of papers on the technique, but we're publishing a lot more, specifically low field optimization for the prototype we're building, and this multi-messenger astrophysics that I mentioned. And so there's a lot of new things coming this way. So the project has been very interesting collaboration of people from across the world who are all interested in relic neutrinos and realizing this experiment, and continue to make interesting project. Thank you. That's all I have. Thank you very much.
Thanks, Chris. We really are looking forward to see your bird of prey in action.
That's right.
So let me open the floor to any questions. Or comments. Well, I have a question. So when do you expect first results of this to come out?
Well, we're building a filter, and the way we've designed the filter is that we can actually feed the filter by running the same technology in reverse, so we can inject electrons. It's very hard to to inject electrons in a magnetic field from the, that isn't along the magnetic field. And but you can with this technique. So we have a system that we've developed that it brings them in from one side and out the other. And we think we'll have that operational probably in about 3 months. So we're making the iron pull faces now and the electrodes. And that's just to, sort of to help us gear up towards, understanding how the capacitances have to be set to be able to dynamically set it. So ultimately, we have to change the voltages. There's only really a scale factor we change. We have to change it on the scale of a millisecond. And it doesn't have to be ultra precise, but it has to be precise enough to keep the electron on its track. So I would say the R&D program for that is another year beyond that to sort of understand how to make the filter respond in time. And concurrently, the RF system, we have a nice system that allows us to just put in a kind of penning trap system where we just keep an electron in orbit and measure its radiation. That's coming along well. I think that we'll have interesting results, I think, already about a year and a half from now. But it'll be mainly on measurement of the tritium endpoint spectrum. The big step for us would be to go to the large tritium mass. And it's actually kind of daunting. I didn't talk about it, but the Catron experiment only uses tens of micrograms of gas. And so our method of putting things on surfaces is a much more stable way to have a large mass, which is on order grams of tritium, but it's a lot of surface area in the configurations we have. So we're hoping, I would say, on the timescale of 5 years, to have a really substantial mass system, if not up to 1 gram, but hundreds of milligrams. And there, we would have very precision measurement of the neutrino masses, the hierarchy, and then there's actually a lot of new theories beyond the standard model theories that would produce a lot of right-handed neutrinos through frictional methods of dark energy and whatever. We would knock out a lot of new physics, late universe things. There's also, theories in which the neutrino doesn't live forever, that on the scale of billions of years, it decays into something. So there is a scenario in which there are no neutrinos left in the universe. So I think we're very happy that the theorists are working with us to help us sort of figure out what kind of benchmarks we need to try to achieve. But it's not a quick experiment. But what we believe is, and if we don't work on it and continue to sort of focus on the experimental challenges, it's something that we'll never realize. And if you think about images of the early universe, there are not that many to be had, and this is one of the ones that people have wanted to achieve for a long time now.
Indeed, all very interesting. I see some hands are raised. Are there any other comments or questions?
I have one.
Please go ahead.
So you mentioned that the neutrino background, so to speak, is a dipole. Is there going to be that reminds me of the redshift effect that you get from the motion of Earth and the Sun around our the center of our Milky Way? Is that going to be in the same direction, or is there an expectation of which direction the dipole would be?
No, the dipole that comes from the peculiar motion with respect to the CMB rest frame is really, is changing at the, micro Kelvin level, sort of the integrated power of RF that you're picking up. That kind of shift is not visible when you detect neutrinos. It's only visible in a tiny way in which it affects the time modulation of the angular spectrum. But because our observable is not in a definite frequency band like we do in the CMB, but is really a counting of neutrinos, so if the neutrino had a momentum where in the Fermi-Dirac distribution, it depends on the momentum over t, whether it's 4 times q over t or 1.5 q over t, it all looks like a neutrino to us. Even the capture rate, it turns out, goes like cross-section time velocity. So the dipole that we would see is not really from that motion. It actually is just that a K mode of roughly 0.05 inverse megaparsec, that the anisotropy just gets amplified going through that K mode, and that's why we would see more neutrinos in one side or the other. So it really, those anisotropies are really direct probes of the primordial perturbations. It's just, we're actually about to publish a paper that shows the line of sight technique for the anisotropies like it's used for the CMB, and it's actually quite interesting. I think the dipole and the quadrupole moments are the things that we can measure best because we're not going to be counting a lot of neutrinos, but those already have inflationary modes in them.
That's fantastic. I mean, dipole is the easiest thing to pick up, so that's so thank you for answering that. That was wonderful. I was nodding here, but you couldn't see, so.
Okay, thanks for the discussion. Any other comments or questions? I don't see any. Then let's thank the speaker, and it was in a very nice way to begin our colloquium series. Thank you, Chris.
Thank you. Thank you for inviting me.
Thank you. That's terrific.
Thank you.
Okay,
Thank you.
thanks then.
Thank you.
Okay, thanks. Let's start the meeting then.